Gnanam Paramam Dheyam. Knowledge is supreme.
In the last lecture, we saw some examples of fields. In today's lecture, we will see more examples of fields, and more generally, we will see some examples of rings also. So recall that last lecture we saw the field of rational numbers, field of real numbers, field of complex numbers. So Q, R and C, Q is a subfield of R and R is a subfield of C. In addition to these standard number systems that we study in schools and colleges, in addition to that we have seen these modulo operations, Z mod P, where P varies in the set of prime numbers. So this is a family of finite fields. These are so-called finite fields. They are finite sets, and on that there are these congruent mod P is a binary operation. More generally, I will show you there are other examples of finite fields as well. But before I do all these things, I need more general examples of rings. The only examples of rings we know now so far are, apart from these fields, the ring of integers. This is ring of integers. And I want to construct more examples from the given examples. That will always be our strategy, to construct more examples from the given examples. So this process will be natural in some sense. So first of all, if I take instead of P any n natural number, last time also, so this Z mod n, Z modulo n, this is also a ring. It's a finite ring. So in general, when one says ring, R is a ring, that means R is a set and it had two binary operations, addition and multiplication, and these multiplication and additions are connected by distributive laws. And obviously R with the addition, like in the case of fields, this is an abelian group, and R with multiplication, this is only a monoid. So remind you, monoid means a set with a binary operation which is associative, and it has a neutral element, and that neutral element is usually denoted by 1, R, or simply 1 when there is no confusion, and the additive identity is denoted by 0 R, which is also denoted by 0 when there is no confusion. So this is a ring, and one says when we have two rings, then usually one compares them like a set, like we were comparing the sets by maps. So these maps should not be just arbitrary maps, but they should be compatible with the ring structure. Ring structure means these two binary operations, plus and multiplication. So when I have two rings R and S, rings, okay, before I go on more generally, when I said rings even earlier, I always mean commutative. That means anyway the addition operation is commutative, but in addition to that, the multiplication operation is also commutative. And we will also assume always that ring has always multiplicative identity. Ring always has multiplicative identity. Multiplicative neutral element. That means one always exists, one R exists always in our definition. This is a standard assumption. I will not keep saying again and again. All rings we will consider in this course will be commutative rings with unity. That means multiplicative identity. When it is not the case, I will specify it explicitly. So when we have two rings, one R and S, so remember that this has addition and multiplication. So does this also has addition and multiplication. But we are not going to make distinction between the notation because otherwise it might become more and more complicated to write it. So a map between the set R to S is called a ring homomorphism. Actually, what I am doing right now is a part of my prerequisite I want to assume in this course, but for the sake of completeness, I want to recall some basic definitions. This means one, so this is called phi, is a ring homomorphism. One, that means as a abelian group, so R plus is called the additive group of R and S plus is called the additive group of S. If I think of this phi as a map from this abelian group to this abelian group, it should be a group homomorphism. That simply means that this phi restricts the addition. Phi of A plus B equal to phi A plus phi B for all A and B in R. So remember, while writing, one should be clear that when you write this plus, that means you are adding in R with respect to this plus operation, and when you are taking the images and adding them, you are adding in S. So that means this plus, though they look the same symbols, this is in R and this is in S. So this is clear from the writing. We cannot be going specifically this is in R and this is in S, otherwise we will not lead to much material in this course. So second one is, it also respects the multiplication. So R dot to S dot, the same phi, is a monoid homomorphism. Monoid homomorphism means it respects the addition. So phi, multiplication, phi of A times B equal to phi A, phi B for all A, B in R. And again, I don't only just know the last time I will say that this multiplication is in R, this multiplication of the images is in S. In addition to this, usually also it is assumed that phi of 1R equal to 1S. 1R means a multiplicative identity in R and 1S means multiplicative identity in 1R means multiplicative identity in R and 1S means multiplicative identity in S. This also I will drop eventually. I will just simply write phi 1 equal to 1. Usually in many books this is not assumed, but we are assuming this. So a map between R to S satisfying both these properties is called a ring homomorphism. For example, so any concept we should be supporting by examples, right? For example, let us take our ring Z, and we have this ring Z mod N. This is modulo operation here, this plus dot plus N. You remember and this is this n. This again we should suppress it, but only for today let me just do it. So the map here is just take any A in Z and map it to A bar, and A bar means equivalence class of A under this binary operation congruent modulo n. So you check that, one should check that. So these are examples. One checks that this map phi is a ring homomorphism. So that means what do you have to check? I have to check that if I take two integers a and b and add them usually and take the image this phi, this is a bar plus b bar. But remember, a bar plus b bar is defined as usually add that a plus b and take the remainder of that a plus b. So these two operations are same. That is what we have to check. That I will leave it for you to check. This is for every a and b integers. So that will mean that this phi respect the addition plus. So strictly speaking, I should write suffix n here, but I will not do so. And also this map usually I will come back to more of these types. Similarly, we will also have to check that phi of AB equal to AB bar, which is A bar dot B bar, and this dot is actually modulo n. So this is a very natural example of a ring homomorphism, and this is not so special. Soon I will give you more examples of this kind. But second thing I will leave it for you to check. Every ring homomorphism from Z to Z, let us say Z to Z. Now I drop that plus dot etc. etc. Z to Z. If I have a ring homomorphism, then what can it be? Let us try to analyze. So first of all, note that by our definition, 1 has to go to 1. So phi 1 is 1. Moreover, if I take any integer n, if n is positive, n is a natural number, then phi n, which is phi of 1 plus 1 plus 1 plus 1 n times, this is n times, and when I apply the condition 1 that it respects the addition, this will be phi 1 plus 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 phi 1 n times. So that means what we noted is phi of any n has to be n times phi of 1. That means this phi is uniquely determined by the image of 1, which is 1 only in this. So this is n. So that means we check that the only ring homomorphism from Z to Z is identity map. So the only ring homomorphism from Z to Z is the identity map. Which is denoted by IDZ. This is the map Z to Z. N goes to N. So that is only. In fact, why this? In fact, more generally, if R is any ring, then there is a unique ring homomorphism from Z to R. And it will be, obviously, it is determined by, if you call it phi, phi, that is uniquely determined by phi of 1. Phi of 1 uniquely determines phi. In fact, if I take any n, phi of n will be equal to n times phi of 1. Remember, n times phi of 1 means phi of 1 plus phi of 1 added n times. When I say when n were negative, then one should use the additive inverses of this one. So this is when n is bigger equal to 0, and when n is negative, then it is in fact n of minus phi of 1. Remember, minus phi of 1 makes sense in the ring because it is the additive inverse of phi of 1. So this is very important map. I will soon use it. I will soon use this to define something about the field. Anyway, so we have ring homomorphism. So ring homomorphism in every subject, like if you are studying group theory, then you use group homomorphisms to compare two groups. If you are studying ring theory, you use ring homomorphisms to compare rings. If you are studying field theory, then you use homomorphisms of fields. Homomorphisms of fields are nothing but homomorphisms of the rings. So you compare them. If you are doing only set theory, then you say maps to compare the sets. Okay, so one more example of a natural ring I want to construct. These are so-called polynomial rings. These are polynomial rings. So first of all, I want to spend couple of minutes for polynomials. So polynomial means what? Polynomial means an expression like this. An x power n, where this a1 to an, a0 to an are elements in a ring R. So these are polynomials with coefficients in the ring R, in a ring R. Is an expression like this. Now one may say, what does one mean by expression? So one easy way to think about them is, you see, if you know the coefficients, you know the polynomial, but you should know the coefficients and their positions. So which coefficient goes where? So one way to think about them, instead of this expression, think about a tuple a0, a1, an, and dot dot dot. It is not a finite tuple, it is a tuple, or actually one should say n tuple. That means the components in this tuple are numbered by using the set of natural numbers 0, 1, 2, etc. n. So this tuple, I should have written here 0, after that 0, 0, 0, 0, all the way. So this tuple has entries, these are the components. So this tuple is an element of R, their entries are in R, and their n tuple is denoted by like this, Rn, R power n. So that is just a map from n to R, but we have more than a arbitrary map, we have only the finitely many coordinates of this tuple are non-zero. That I want to write in the notation like this, round bracket here. This means there are n tuples with entries in R, and only finitely many entries are non-zero. So eventually after some stage all the entries will become 0. So either think like this or think like expression like this. So this position A1 you put a symbol x. This position you keep increasing the powers of x. So that is typically one thinks about polynomial. Also I want to remind you that when I said yesterday that the quadratic equations, cubic equations, biquadratic equations, etc. It from there to progress to the arbitrary polynomials, it took longer time because there was no notation for polynomials. People at that time were not very careful in notations and also meanings and so on. So the person who did this first systematically was Vitae. This was in 1500 something, 1591. He was a French mathematician. More about this I will say when I prove some result. So now, if you have two polynomials, so polynomials are usually denoted by f of x. When there is no confusion, we will only write it f. F is a polynomial. That means expression like this. Or if you want to think like a coordinates. But I would recommend we start doing this because we were used to that even from earlier curriculum like school, colleges, etc. So that's a polynomial. Where the last coefficient is non-zero, of course we only have to note up to where it is non-zero, and after that there are zeros. Now an, the first time n, the last time n it is 0, that n is called the degree of this polynomial. So this n is called the degree of f if n is non-zero and all other terms are 0 after that. Am is 0 for all m bigger than n. Then this is called a degree. Let me remind you, degree of what is a 0 is also polynomial. There is all the coefficients are 0, is a 0, 0, 0 tuple. So that is called a 0 polynomial. So 0 polynomial is same thing as 0. I will write it 0 because all coefficients are 0. But this is also the tuple 0. And the degree is not defined then because what was the definition? There is only the last one which is non-zero. But there is no non-zero entry in this. So this degree of a 0 polynomial is not defined. That one should note carefully. So degree of 0 is not defined. So when you have to, these are also called polynomials over k. Polynomials over k, over R. And the set of all polynomials over R is denoted by set of all polynomials over R. This set is usually denoted by Rx, R square bracket x. And remember my writing always variable. This x is called also variable. X is a variable or indeterminate. Variables and indeterminates are always denoted by capital letters x because small letters x are used, you will see, they will be used for evaluations. So, and the square bracket is also denoted for the polynomials. Later on you will say they are rational functions. So now on this set there are two natural operations, addition and also multiplication. So that it becomes a ring and then we will say that it is a polynomial ring over a ring R. And what are these operations? So that means what? I have to write, if I have f is a polynomial, if I have two polynomials f and g in Rx, then I have to tell you what is f plus g. This is what? So it's very simple. You take f and g and think of them as tuples. So they are two tuples with they are numbered by the natural numbers and only finitely many are non-zero. So I will add the corresponding coordinates and put them as the coefficients, or think of this new tuple. So that is called the f plus g. So let me write it only once. So if I have f is like this, a0 plus a1x etc plus am x power m. This am is non-zero, so m is the degree of f. G is another one, b0 plus b1x plus bnxn, where bn is non-zero. Then how do I add f plus g? That is, you add the corresponding coordinates, a plus b naught, a naught plus b naught plus a1 plus b1 x and so on. Now this may be bigger, that may be bigger, so add corresponding coefficients. So you will, if they are equal, then you will land up at the same position, otherwise it will go on to the next one. So that is the addition of polynomials. Now one has to check that this addition is associative and the polynomial 0 is the additive identity, and with respect to plus, these polynomials form an abelian group. So this is abelian group. This I will not check, I will simply say check. One is to check. Similarly, there is a product notation, that is given f and g like this. I want to define what is f times g or f multiplied by g. This is little complicated. So it is again, so f is like this, g is like this. Then I want to write f times g. So I will write in this notation c1x plus c r x r. Now I have to tell you what are c's in terms of a's and b's. So ci is, by definition, you take summation over k plus l equal to I ak bl. Now remember, this multiplication is in R and the sum is also in R. So this definition makes it a multiplication on this set, and with respect to that, now I will simply directly say that this Rx with plus and the multiplication I have defined, this is also commutative ring, and this ring is called a polynomial ring. Over R. Or also one says polynomial ring with coefficients in R. So we have extended the definition of addition and multiplication from the ring R to the polynomials. So, and we have the natural map from R to Rx, namely A going to A. These are called the constant polynomials, and this is a ring homomorphism. Not only arbitrary ring homomorphism, but this ring homomorphism is injective. That means it is injective as a map. That means different elements go to different images. Okay, we will continue our lecture after the break. Thank you.